Okay, so let me briefly go over what we were doing last time. Um, so we started to take a look at these steps that we've been following for the method of weighted residuals. So let me actually switch this to better zoom. Okay, so some of the methods, some of the steps that we said were going to be whenever you are trying to solve any differential equation, take that differential equation, multiply it with some u bar function, and integrate it over the domain, let's say from 0 to L. The second step was to integrate this this functional that you get by parts so that you can balance out the derivatives. And we went through all these steps for this Ritz method. So this was the equivalent form right here. So we take the governing differential equation, multiply it with u bar, and take partial derivative, integrate it by parts once, and we get this new functional. So this new functional is nothing but the principle of virtual work. So the third step was to try to approximate your solution. So we said we will introduce an approximation which will, so the real displacement is ux, and the approximate displacement is also a function of x, but it is going to be a sum of linear functions, a linear combination of some functions. And we said that these functions have to be of a certain type. So we talked about, let's see, where was that? Square integrability and all that. So, and then finally we started to take a look at this example last time. So in this example, we said that the functions that we are going to choose are these polynomial functions. So if we express our displacement in terms of a linear combination of all these functions, then we'll express that displacement in terms of those and the virtual displacement u bar also. And then if we plug in those expressions in our virtual work form, then what we will get is this equation that says for all a bar, if we make sure that this bracketed term is 0, then we've solved the problem. That is, all the equilibrium equations are going to be satisfied in a weak fashion. And again, as long as you don't make any approximations, the weak is exactly same as the strong form. So, okay, so let me ask you this. These are all polynomial functions from 0 to L, linear, quadratic, cubic, and so on. Which space do these functions belong to? So if you go back and take a look at the first page of this chapter, we talked about that these functions at least have to be square integrable with the first derivative of those functions has to be square integrable. So we chose last time all these polynomial functions. Um, are they continuous functions? Do they belong to C0? They are continuous over 0 to L, right? So they are at least C0. How about if we take their derivative? So let's, where was that? So if I take these derivatives, if I take the derivative of all these polynomial functions, I will get another polynomial that would be 1 degree lower, right? So how about that? Is that going to be, is that derivative also a continuous function? Yeah, over 0 to L, that derivative is also continuous. You take another derivative, that is going to be another polynomial of a lower degree, right? So all those functions that we chose last time, they are actually called C infinity. What that means is you can differentiate them infinitely many times and you will still get a continuous function. So that is way down into the list, C infinity. And I told you last time that you can restrict the space of functions that you are choosing by going in this order. So this is the last line of functions that you get. And let me go back to this. So another thing to note here is that as soon as you take the derivative of this first function, you get a constant, 1 over L, right? You take a derivative of that, it becomes 0. 0 is also a continuous function, right? So after that, you can keep on taking derivatives that wouldn't matter. All right, so then you write out your H prime vector in this form, in the column vector form and the row vector form. You form your stiffness matrix. Similarly, we calculated the load vector, and we took a look at how it behaves. So yep. We'll actually get to that a little later in the course. It is important for you to know whether if you choose to add more and more functions, is it going to converge or not? I'm not going to ask you. So all this C infinity and this function spaces and all this business is a little more mathematical, and there's a huge field called functional analysis on this. So I'm not going to expect you all to know all those functional analysis terms, but at least you should be able to follow what we are talking about in the course. And the types of homework problems that I'll give you it should give you an indication of what types of questions you might get on the midterm. Okay. So we said that this was the exact solution for the displacement. This was the exact solution for the displacement, and this was the exact solution for the stresses. And this was the stiffness matrix that we coded up last time using our one-dimensional approximation. So that's the stiffness matrix, that's the load vector, and if you plot, now take a look here that I'm just choosing k1, 1. So that's the first term approximation. If you plot the first term approximation, you get a linear response. This is expected. And last time we did not plot the stresses, so here's the plot for the stresses. And if the displacement is linear, the stresses have to be constant, right? And we also showed that last time, if you choose the first two terms, meaning the linear and the quadratic term, then you end up with the exact solution. So the Ritz method with two terms gives you an exact solution, this green curve right on top of the blue curve. So since the exact solution has only quadratic terms, the Ritz method converges exactly to that. And then if you keep on increasing the order of the polynomial, it wouldn't matter because you've already reached the final stage. So this is about where we were last time. And so what I'm going to do today is we'll take another example. Now this example, it's the same problem that we are trying to solve, but we'll choose a different approximation basis. Yeah? Mm-hmm. Yeah, I think I missed the derivative on that too last time. So you can. No, it need not be equal to 0. Only if you choose h0 as a constant function, then its derivative is 0. It's in the f, yeah. Yeah. And actually, let me also point out last time when we were correcting the derivatives, so we were correcting the derivatives on the k, on the stiffness term. We said that this needs to be h prime, h prime. It also needs to be h prime here and here. That's the h0 that belongs to the f term that we were just talking about. Okay. All right. So for the one-dimensional finite elements, we are going to solve the same problem. This bar with body force under self weight and some interaction These were the parameters that we used last time. And we said that we can convert this strong form of the equations to a weak form by just taking this equation, multiplying it with the u bar, and integrating it with parts. So if you do that, you will get this g, which is nothing but internal virtual work minus external virtual work. And the problem in the weak form says that find a function u, find the real displacement, which is an element of this h1 space. What is that h1 space? 1 means the first derivative, and h means square integrable. So the first derivative has to be square integrable. And not only that, it has to satisfy the essential boundary condition that displacement at 0 has to be equal to 0. And if you can find u such that this functional is 0 for any u bar, for all u bar, which is in the space of h1 0. And this 0 was denoting that this u bar at 0 is equal to 0. So this is a little different from the essential boundary condition. This is called the homogeneous essential boundary condition. So now we will introduce our approximation that u, now this is a scalar function of a scalar variable. U of x is a linear combination of some shape functions. And these are all the unknowns that we want to find out. These h functions are functions that we will choose, that will be known functions. So this is the approximation if I write it out in a vector form. So this is a row vector, so I'm calling it A vector transpose. This is a column vector, so this is H vector where each term is a function of x. Okay? And we also talked about that when we use a Galerkin approximation, we choose the same set of functions for the virtual displacement also. So u bar of x is also expressed in the same way. But in this case, there is this difference of a bar. So these constants are different here, but it's the same h functions here. And the real difference, so when you plug all this in, you can write out your g function that you had before in this form. And we can easily solve this for a, and that would mean that we have satisfied the equations weakly. So in the finite element basis functions, what we choose as the basis functions are as follows. So let me call these functions h0, h1, h2, h3, and h4. And so the first function that we choose is this. This is the value here is 1, and it is a very local function. So what we've done is we've divided this length into some n parts, and the way I have drawn, it seems that all these parts are equal, but they need not be equal. Okay. So just to keep things simple for today, we'll choose that we have divided it into 4 equal parts, but obviously we can divide it into any number of parts. So the second function is this function that goes to 1 at this point, and it's 0 everywhere else. Okay. So if you draw all these functions, they are called hat functions. And the next one is this, and finally you have this. So these are shape functions or finite element basis functions. Now compare them with what we were doing last time. We said last time that the shape functions that we will choose are going to be something like this. Linear all the way through from 0 to L. So these were global basis functions. Global means that they span the entire domain, 0 to L. But today, in the one-dimensional finite elements, we are choosing these shape functions in a little different way, such that they are only local. They are non-zero only at a small, in a small region. So if you do this, you can, now let me ask you, which space of functions do these belong to? If I take the derivative, let me draw the derivative here. This is h1 prime, oh sorry, this is h0 prime, h1 prime, h2 prime, h3 prime, h4 prime. So what would the derivatives look like? For h0, it will be simply 1 over length of element. Okay, and it is 0 all the way through. Sorry, this should be a negative. So it should be negative 1 over LE. So minus 1 over, let me say LE, where LE is L divided by N, where N is the number of parts that we have divided this bar into. So in this case, we have divided it into 4 parts. So N here is 4. And LE would just become the small length, which we will call element. Okay. So similarly, the other derivatives are going to be, I don't know. So this is the derivative positive in the first element and negative in the second element and 0 everywhere else. Similarly, this is positive here, negative here, and 0 everywhere else. This one is positive here, negative here, and this one is positive here. Okay. So these are the derivatives. Now, are these derivatives continuous? These derivatives are not continuous because they jump at every element boundary, they jump. Okay, so these derivatives are not continuous, which means that if you go back to the first page, then it is certainly not C1. These functions that we have just chosen, these functions are not C1, meaning their derivatives are not continuous. How about, are they integrable? So if we look at these functions, if we square them and try to integrate them, will we get a finite value? How many think we'll get a finite value if we square them and integrate them? Okay, so most of us think that it will be finite value. So that means that it is a square integrable. It is a function with first derivatives that are square integrable. So indeed, all of these functions belong to h1 over 0 in the interval 0 to L. Okay, so this was the minimum requirement that we had for our weak form to be defined. So now let's try to write out a mathematical expression for these functions. So let's say hi. So if we write this as x minus xi minus 1 over xi where all these values are, this is x0, x1, x2, x3, and finally x4 is L. Okay, so all I'm doing here is I'm expressing the value of this function. So let's consider h1. h1 is 1 at x1 and it starts from 0. So I can simply write that function in this interval using this formula. Does that make sense? So let's say x, if I choose the value of x somewhere in this interval, then xi minus 1 would be this point. This would be the length of this interval, and divided by this entire length, that's the function that describes this h1 in this interval. Similarly, this function is the equation for this part of this hi function. I hope you are able to see that. So, and then similarly, if you try to write out the derivatives, those derivatives, h prime, they can be written as minus 1 over LE in the first half, and plus 1 over LE in the second half. So I'm running out of space here a little bit, but so if I shift this, okay, this is in the region when x is an element of xi minus 1 to xi, and this is in the region where xi to xi plus 1. So each shape function is defined over this kind of an interval. So we divided this interval into two halves, and similarly you have those two halves here also. So you have xi minus 1 to xi and xi to xi plus 1. So now if we start to put this back into our weak form, let's see what types of stiffness matrix and load vector is we get. So for the stiffness matrix, we said that it needs to be integrated from 0 to L, and it has to be H prime and H prime transpose dx. So this is nothing but integral 0 to L H1, H2, H4, and H1, H2, H3, H4. So if we integrate this out, we will get a 4 cross 4. If we multiply this out, we will get a 4 cross 4 matrix. So, and these are all primes. H1 prime, H2 prime, H3, 4, and all primes. So if we multiply this out, what we get is, I'm just talking about this integral now. So let me remove this equal to sign. So what we will have is H1 prime on the diagonal, H2 prime on the diagonal, H3 prime on the diagonal, H4 prime on the diagonal. Okay, and the reason I'm doing this is so that you can see what terms you actually need to calculate in 1 dimensions, and this will be true for 2 dimensions and 3 dimensions also. So how about H1, H2 prime? So if you take a look at this, this is the H1 prime function and H2 prime function. That term will go into the 1, 2 column of that stiffness matrix. So if you see H1 times H2 prime, the only common region where they're both non-zero is this element right here. So there will be a component coming from H1, H2 prime. But from H1, H3 prime, there won't be any component because H1 prime is non-zero here, H3, so they don't overlap where they're non-zero. So the only non-zero component in the first row is H1 prime and H2 H2 prime. H1 H3 prime is 0. H4 prime is also 0. And since it is symmetric, I'm not going to even try to look at the lower triangular terms. How about H2 prime? So if I pick H2 prime and try to calculate which are all the functions that contribute to the H2 prime term, we see that only the H1 prime and the H3 prime have a common region with H2. So these are the terms that will be non-zero for the second row. So that second row will be H2, H3, and this term would be 0. This is all symmetric, so let me just write this as symmetric. And finally, you will see that H3, H4 prime is the term here. So the thing to notice here is that this stiffness matrix is a tridiagonal matrix, meaning that there is a main diagonal and there is one above and one below. Everything else is 0. So those types of matrices are called tridiagonal matrices. And in order to calculate these terms, what we need to calculate is basically KII. And if you do that, we can simply write that as 0 to L, C. And we know that H prime is what we just calculated here. H prime is minus 1 over LE and plus 1 over LE. So if we write that out, and we should also change the limits since the functions are non-zero only in a small region. So xi minus 1 to xi and minus 1 over LE multiplied with minus 1 over LE. And there is no summation here. So this is just to denote that it is a diagonal term here. So if we do that, what do we get? C x going from xi minus 1 to xi over LE square. Does that make sense? And then what we get is C times C over LE, because the numerator is nothing but LE. It is the length of that element. So this is the main. These are the main diagonal terms. Now there is the off diagonal term I. Let's say I plus 1. So we are trying to calculate, let's say 1 comma 2 now. So what that would be like is integral from xi to xi plus 1 c of minus 1 over, or actually it should be plus 1 over LE, but it wouldn't matter. So this is what we get for the off diagonal term. Okay, and if we do the same type of integration, we will see that it will come out to be minus c over the length of the element. And for the main diagonal terms, here what I did was integral from xi minus 1 to xi, which was any. You take, if you're calculating for I, you're doing from, then you take the integral from I minus 1 to I, and similarly you also need to take the integral from I to I plus 1. So actually this term will have a second part. Plus integral from xi to xi plus 1 of the same thing, or actually the positive thing. And this will also be equal to C over Li. So when you sum them up, the total would be twice C over Li. And all that you have to do now is to arrange those terms into the big stiffness matrix. And if you do that, what we get is C over L, we'll take it out common outside, and on the diagonal you will get 2, 2, 2, except the last term, which will be 1. And the reason that the last term is 1 is because for the last element, if you take a look, this last element right here, this has only the positive, this only 1/2 of the function. So this, when you integrate this part, you don't have the negative part, that the second part that we added a little later. This is a lot of algebra that I'm trying to show you all, but try to follow and just try to get an idea of where this all is going. So in the off-diagonal terms, all that you will have now, since we have taken out C over LE common, we will have -1, -1, -1, -1, and the rest are all 0. So this is what our stiffness matrix looks like for a one-dimensional finite element basis function, where we have divided it into 4 elements, and they're all equal. All those 4 elements are equal. So similarly, if you try to imagine, if we divided it up into 10 elements, we would have a 10 cross 10 matrix where all the diagonal terms would still be 2, and the off diagonal terms would still be -1, and the exact same structure would follow. The only difference would be that the length of each element, since we have divided it into 10 parts, would be smaller. So now that we've found out this stiffness matrix, we also need to find out F, the load vector, which is 0 to L, H vector times the body force, dx, plus H vector evaluated at L and traction at L. So let me try to write this out again into this form. This is 0 to L, and all these H functions are right here. In this particular problem, our body force B is a constant. Okay, so since the body force B is a constant, I can take this body force B out of the integral, and all I'm trying to integrate here would then be H vector dx, body force is out common, and this vector would be the same H vector, the shape functions evaluated at L and TL. So what does this look like? This is nothing but the integral of each of those functions over the entire domain. So what is the integral of each of those functions? Let me go back to this place. What is the integral of H1? Integral of H1 from 0 to L, area under the triangle, which would be half times base, which is twice LE, times height, which is 1. So which would simply be LE, right? So what we get here is LE, 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 and the last one would be LE divided by 2, because again, we have only the half of that function. So this area is half of the rest of them. So, yep. Oh, H0 we already said, since we said that U0 is going to be 0. So did I not point that out somewhere? Oh, yeah, I think I probably forgot to mention. This H0 is the one that we require to for the essential boundary condition. Okay, but since in this case we said that U0, that there is no displacement at the fixed end, therefore this H0 or the constant that you multiply with that is chosen to be 0. That's why this is not there. So yeah, in this case you can actually neglect this first H0. We are starting from H1, H2, H3, and H4. These are the 4 shape functions in this problem. And then how about this term? These are all multiplied with b. What does this term look like? What is the what is H1 evaluated at L? H1 evaluated, sorry, this is H1 evaluated at L is 0, H2 is 0, H3 is 0, H4 is the only one that is 1 at L. Okay, so what we should get here is 0, 0, 0, 1 times TL, and if you sum that up, what you would get is LEB, 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 LEB divided by 2 plus TL. Does that sound okay? Okay. So now once again, all you have to do is to go to try to solve. To solve this, all we are going to do is A is equal to K inverse F. Okay, and once again I've coded up a small MATLAB routine for this. So let's take a look at what this solution looks like. So this is the stiffness matrix that we've just coded up. Okay, it has 2 on all the diagonals except the last one, which is 1 again, and -1 and -1 on your off diagonal terms. Everything else is 0. So if we run this, this is the exact solution for the stresses, and this is the exact solution for your displacements. And now MATLAB will calculate the value for K. So this is your stiffness matrix. It's 4 cross 4. It is symmetric and it is tridiagonal. Okay. This is the load vector. So the load vector is also a 4 cross 1 matrix. Here is what you calculate your solution, and I'm adding this 0 to the solution because we know that the first node of our problem is fixed at 0. So that's now this next part is for calculating the stresses, and this is a little different than the one that we did previously. Previously in the Ritz method, if once you calculate your scalars, your coefficients A, you can simply plug them into the expression for the stresses and you will get that. But this finite element basis functions are a little bit different. Here, if you take a look at this basis functions, the shape functions are linear within some range, but the stresses, their derivatives, they are actually constant over those ranges. So we actually need to be careful about calculating the stresses. So let me not go through this loop, and let me simply plot here. So you can see that these blue dots, they are right on top of this curve, this black curve that was the exact solution. And once again, this, at least in one-dimensional finite elements, you will see that the finite element basis is able to reproduce on the dot the exact solution. Okay, so if you were to choose more and more elements, your solution would keep on getting better and better. Okay, and finally, if you plot the stresses, the stresses look like this. And this is again a characteristic of the finite elements, because we are assuming that the finite elements is going to behave linearly in a small range, that the displacement is approximated with a linear shape function in a small range, which obviously means that the stresses are going to be constant in that range. So again, you can see that this method, finite element, which is a special case of the Ritz method, tries to do its best. And once again, if you keep on including more and more elements, including more and more points, these approximations will keep on getting better. And later on, we'll also see what is the rate of convergence. So if you double the number of shape functions, this error will actually go down by 4, but this error will actually go down only by a factor of 2. So the derivatives, the rate of convergence to the exact solution in the derivative is lower than what it is for the displacements. Okay. I have about. Are there any questions on any of the steps? So once again, all the steps that we've done here are exactly the same that we did for the Ritz method. So all that we did was we took our governing differential equation, integrated it by parts, but this time we substituted in a different approximation. If you use yet another approximation, you will get some other result. Okay, and the solution part is nothing very special. So this was the one-dimensional finite elements, and this was again a case of a Galerkin approximation, meaning that we chose our virtual space the same as our approximating space. There are a couple of other types of weighted residual methods, and let me, in the 10 minutes that I have, talk a little bit more about this. Yeah. Okay. Mm-hmm.
I think you apply the boundary condition first.
Yeah.
And you neglect the H0.
Right.
So I think now H prime should be essentially that sign, right?
Which H prime?
First one should be positive 1 over L and this one, because we.
So this is H0. This was the H0 function we said that was going to be 0. This was the one that takes care of the boundary condition.
So in the expression here.
In this one?
Down.
Down?
Yeah, H prime.
Here?
Yeah.
The
next one should be negative because we neglect that H0.
You're right. Yeah. All right, thank you.
And my question is that because in final element, most of the time we first form the stiffness matrix and then apply a boundary condition. Is it better to?
So yeah, that's also the way that we will do, but I was trying to make a link between the Ritz method and the finite element method, how it is a special case of a Ritz method. So you will see that obviously this is not the best way to implement on a computer. If you want to implement this on a computer, you don't want to be calculating all these stiffness matrices by hand, and you don't want to be enforcing your essential boundary condition right up front by choosing a certain H0. So what we'll do when we code this up, from next time, I'll show you the one-dimensional finite element code structure, meaning how can we arrange these calculations in such a way that it's easier for us to calculate and it's easier for us to code it up and try to find the solution. Okay, so this was just to make a link between the one-dimensional finite elements and the Ritz method. So there are these other types of weighted residual methods also that I was just telling you about. So just to recall, when we set up our functional, we said that the functional is going to be 0 to L and U prime times our governing differential equation. So governing differential equation is nothing but div S plus B, and you can also add the boundary term if you want. So this would be actually negative G as we have defined before. So just to be consistent, I'm multiplying it with a minus sign there. TL minus sigma at L. So this was the weighted residual that we had defined earlier. And in the first one that we've already taken a look at is the Galerkin approximation. Here, in this Galerkin approximation, we choose u bar, this function u bar, we choose it equal to whatever approximating function that we chose for the real displacement. So in this case, let me also introduce the approximation here. We normally choose our approximation to be some a vector transpose times some shape functions. So this is our approximation for the real displacement. For Galerkin, which is also actually called Bubnov-Galerkin method, we choose our, and again, I'm introducing this. This is something that we did last time. We are approximating our real displacement with a discretized version of the displacement, which can be expressed as a linear combination of some shape functions. Our virtual functions can also be discretized with the same shape functions, but with different coefficients here. So if we do that here, then this is called the Galerkin approximation. On the other hand, we have something also that is called a Petrov-Galerkin method. So for a Petrov-Galerkin method, our u bar of x is approximated a little differently. This is approximate, this is approximate. U bar at h, which is equal to the sum of the same scalars, coefficients, but now we are going to multiply them with a different set of h functions. So just to differentiate from the earlier basis functions, I'm including this bar on top. So these are different basis functions. So if you choose a different basis function for your virtual displacement and and a different one for your real displacement, it falls into the category of Petrov-Galerkin, which is not that commonly used, but there's an important point here that the stiffness matrix that you will get in this case, is that still going to be symmetric? Do you think that the stiffness matrix is still going to be symmetric for this? It's actually not symmetric because if you remember, in the Galerkin case, when we substitute this approximation and we try to calculate the stiffness matrix, it turns out to be C H prime transpose dx. But in this case, the K for the Petrov-Galerkin method would be C times H bar prime and H prime transpose. So this stiffness matrix will not be symmetric. So actually, let me stop here, and we can continue talking about this next time, and we'll go over how to actually see a better implementation of the one-dimensional finite elements. All right, so see you on Monday.